so I'm going to present a little update on the Tezos team and community development because we have a great core team working in Paris on the development of Tezos, but there's also a lot of people in the Tezos community which are building great projects. Many people don't necessarily know about these projects, and so I want to give them a shout out after I talk a little bit about what I've been working on. All right, so core team development. Okay, so main axes we're working on right now. One is validation layer and networking. I'll explain exactly what I mean by that. 2 is our smart contracts system and the Michelson language. 3 is documentation. We have a big documentation effort going on. And 4 is proof of stake hardening, which is something that I've been working on personally. So validation and networking. Okay, so validation means that you're connected into a peer-to-peer network, and then someone comes to you and say, you know what, you have a version of the ledger. Well, guess what? I have a better version of the ledger. I have a different head for the blockchain, and you should just like accept my head because it's better than yours. And in Bitcoin, the way that you can verify that is fairly easy. You're going to download block headers in Bitcoin, and the block header is only 80 bytes. It's very small. All you have to do is you compute 2 hashes, you do 1 comparison with the difficulty, and boom, you know immediately if the block is at least plausibly valid. And I say plausibly because you could mine a block on a Bitcoin network that's invalid and that has a valid proof of work, but if you do that, it's going to cost you about 125,000 Swiss francs around current prices. So very, very expensive to do that. So this is a massive anti-spam device. Like creating a fake block would be very, very stupid because it can be seen immediately that it's fake, and it's very, very expensive to make one. So you're not going to see fake blocks like this on the Bitcoin network. In proof of stake, it's a little harder because you don't have this proof of work, and so seemingly valid blocks are cheap to create, and you can't go around that because that's the whole point of proof of stake. We don't want to be spending 100,000 Swiss francs in order to create a block and add a block to the blockchain. So if it's cheap, what prevents people from creating a ton of blocks and sending you all these blocks, and now you have to validate them? And so in the very, very initial version of Tezos, in the very early days, the way that the protocol worked was to say, well, whenever there's a block on the network, if I want to validate it, I'm just going to validate the entire block. And from a computer science perspective, you could say, well, it's the same thing. Validating a block is constant time, and validating a header is constant time. So, a block is just a little bigger. But a block in Bitcoin is about like 30,000 times bigger than the headers. So the constant does matter. And if you do want to pack a lot of transaction in your block, you're going to have to find a faster validation method than just looking at the blocks. So Tezos tries to have a very generic interface. It's not protocol specific. You should be able to write any protocol. And so we generalize the concept of a block as a series of nested dolls of increasingly larger and larger structure. So you start with minimal headers, and then slightly bigger headers, and then slightly bigger until you have a full block. And for our API, we basically arbitrarily set it at 3. So Bitcoin has 2 levels. There's a header and there's a block. Although now with SegWit, you could argue that there's actually 3 levels in Bitcoin. You would first verify the headers and maybe the hashes of the transaction, and then maybe you verify the signature. So we set it at 3 in Tezos, and so we verify 3 levels. One is the minimal headers. So that's basically a very small proof of work step. So we do have a very little amount of proof of work in Tezos. But the goal here is not to ensure consensus or to give abilities to consensus. It's just to make it a little harder to just create a million block, right? You want to create a proof of work that is comparable to the time it would take to check the header, so that or even larger, so that you have a little bit of a symmetry. But it still makes the blocks extremely cheap to create. The baking signature, which is who created the block in the Tezos protocol, and the root of the Merkle trees, we verify that they're valid. Sorry, that's what it contains. You don't actually verify that they're valid. So you just verify the signature. It's for a fairly small header, and you can verify that pretty quickly. Then we have the full headers, which contain all the operations that affect fitness. So in Tezos, you not only have the signature of the baker, which is the person creating the block, you also have a list of endorsements. So currently we use 16 endorsements. So for every block, there's 16 randomly chosen stakeholders who have to say, I endorse this block seems valid. And that is in a slightly bigger header. So we just do one very, very quick pass. Then we download those endorsements, do another pass, check the fitness, and then we do the full blocks where we take the entire block, verify all the operations, calculate everything, and make sure the chain is valid. And what allows us to do that is, the signature change fairly at every cycle, and a cycle is something like, I think right now I'm trying to set it around 11 days, I think would be a good parameter for the length of the cycle. On our testnet, they're very short right now, but the goal is, in order to test it, but the goal is to make them slightly longer. So we have in the protocol by default something that is sometimes called cementing. I think NXT was calling it cementing, which basically says to your node, if you've been online for a while, you should be refusing forks which are longer than a certain time period. So for example, refuse any forks that's longer than 60 days. Or maybe if you see something like that, then alert the user in some way, like something is wrong. And so once you do that, you basically are able to know exactly which signature you should expect. Now, still notice that even if you have minimal headers, it's still a lot more expensive than Bitcoin, because when you verify these signatures, you see this block, you have to say, hey, is it actually the right stakeholder making the signature? You have to actually hit in memory and look what's going on. Whereas in Bitcoin, you could even verify, you don't need anything to verify the validity of the block. You just need one number, which is a difficulty. You could do it just on hardware very, very easily. So it's impressive how efficient at anti-spam the Bitcoin network is. It's hard to replicate that with proof of stake. So the general principle is you download as little as possible, reject as fast as possible. So in a block, the first thing we do is try to reject it, try to find every possible reason why the block might be invalid, and then if we fail to see that the block is invalid, then it's valid. And like I said, we have this minimal anti-spam proof of work on blocks. It's not 125,000 Swiss francs, but it's not zero either, right? It's probably it's on the order of pennies, but pennies make a difference if you want people not to make millions of blocks. So that validation layer is a big piece of work that Grégoire, one of our engineers, has been working on for a while. It's currently not in our AlphaNet, but the latest thing that he added to the AlphaNet is what we call the pipeline validator, which means that instead of having just like one big function validate all the blocks, there are a bunch of asynchronous calls to different workers who each take a part of the validation and do it after another. So our validation is a lot more responsive. You don't have a peer blocking the validation because we're busy just like validating a very long chain. So that's made the operation much smoother, but I'm really eager for the merging of that piece because it's really one of the linchpin of the development that has been going on for a while, and probably the most technical part that needs to be added for the network to be safe when it goes live. In order to prevent abuse, we also do things on the networking layer. So first of all, peer communications are encrypted and authentified, which means that every peer on the network has a cryptographic identifier. So when you're talking to a peer, you're talking to a public key. That public key can be long-lived, and so you can have some sense of, I've been talking to that person for a long time. They have never hogged my bandwidth. They have never actually sent me bad blocks, or they have never relayed bad transaction. So since I've never actually downvoted that peer, I can trust them. If for some reason they ask me for a lot of blocks, I'm going to give them that. In the contrary, if we have peers relaying invalid information, we can blacklist them. And so we're being very careful about avoiding peer starvation, so that if you're connected to many peers, you don't have one hogging your CPU, hogging your bandwidth. Again, this is something that's a trickier problem in proof-of-stake systems than in proof-of-work systems. There's a complexity cost for proof of stake, which is very real. And of course, there's a penalty for equivocation. So if you create many blocks at the same height, actually, in order to create a block, you have to be bonded. And if you do that, it's detected by other peers. You can say, hey, I've seen the same signature for the same person for 2 different blocks. They're not supposed to do that. You lose a bond. So we can make it very expensive for you to try and create many fake blocks. So in general, we try to take as many precautions as possible. It doesn't prevent people from creating these chains where they have these very low scoring blocks where someone has a very low priority of creating a block and they still create it. But such chains are designed that it takes them a very long time, right? So if you want to create a block that has a very low priority, then maybe you only get to create this block an hour after the previous block. So your chain is going to be not very, very dense. I can say, hey, I have this high-scoring chain, but you look at it, and then it says, well, it has 3 blocks, and then it's next week. So we have all these tricks to avoid spam. I consider that spam avoidance is probably one of the trickiest aspects of a good proof-of-stake system. Spam avoidance and randomness generation. Okay, yes? What the what?
What's the business advantage? What's the advantage to the business use case of this validation?
What is the advantage of the validation network? Well, not having invalid blocks.
No. Versus the Bitcoin that you explained.
Well,
What's
the advantage of
value
yeah.
doing this?
So it's not an advantage. It's just that we are a proof-of-stake system, and so we need to have a more hardened validation layer by virtue of being proof-of-stake. Like the fact that it's cheap to create blocks create a whole bunch of problems that you have to deal with. So it's we pay a cost in complexity by having this more complex validation layer.
Yeah. So basically, you replace one complexity or difficulty system with another one, right?
Yeah.
Yeah. So what I was saying was, you are proposing an alternative to what Bitcoin has, right? In terms of avoiding scam or avoiding this thing. So what's the advantage? Is there something which is better here, or? Well,
yeah, the advantage is that it's the complexity cost you paid once during development, and then you save maybe $1 million every hour. That's what Bitcoin is spending in electricity right now. So if you get a system that's way cheaper that can maintain the consensus for a lot cheaper, I think that's a good trade-off.
Okay, but if it is cheap, that means also the entry barrier is low, right?
The what?
The entry barrier is low.
The entry value?
Entry barrier. The barrier to do,
the value of what? The barrier to entry. Yes, but the barrier to entry is a network effect. Like right now, what's the barrier to entry to Bitcoin? You could create a Bitcoin-like system and then go and convince every miner to merge mine it. And they could merge mine it. Validation of that wouldn't be a big deal. Or you could have a competing chain to Bitcoin, and then once the difficulty is adjusted, it should be the same value to miners to mine one chain versus the other. So really, like hash power is driven by prices, and prices are driven by perception. It's not the other way around. There's a lot of things, like look at Craigslist. Like the value, the difficulty of replicating Craigslist is not the cost of building Craigslist as a website. It's the cost of building the community. It's the cost of building everything else. So these things are selling points. That's how they're defended. They're not defended by the amount of money that goes into proof of work. I mean, maybe I'm wrong, but that's my thesis. Okay. So Ed, by the way, yeah, feel free to interrupt me and ask questions. I think it makes more sense sometimes to ask a question while I'm talking about something rather than wait until the end. So feel free. Yeah.
No more question, please.
What?
Questions at the end.
Questions at the end. Sorry. Okay.
We're running around.
Sorry. Ignore what I said. Michelson and smart contracts. Okay. Calling conventions. So one of the big changes that we're making in Michelson, the current calling convention we have is kind of hybrid. We let you call another contract almost as if it were a function call, but we require stack to be empty. We require you to commit the new value of the storage, but it does preserve the program point. So you're in the middle of the program, but we ask you to have clean your stack and you basically force you to do housekeeping before you call any other contract. And that's a way to avoid reentrancy bugs like the one in a DAO. And it's nice, but it doesn't have really strong theoretical properties, and it prevents you from doing certain things like calling contracts within lambda expressions and so on and so forth. So we're working on a new calling convention, which is cleaner. And the idea is that we don't treat these I said external, I meant internal. We don't treat this internal transaction like from a contract triggering transaction to another one. We don't treat it as a function call at all. What we do is that we have the contract emit at the end a list of operations. It says, okay, I've computed things, I've computed my storage, and by the way, this is a list of transactions I want to make, and they're the same transaction object that you see in blocks. You place these operations in a queue, not a stack. which means that it's going to be first in, last out. And so essentially you get something like an asynchronous model. You can't just like enter into a contract, get a value back, and then continue. You're just basically going to say, I'm going to send information to this contract, and you know, it's going to do what it needs to do with it. If you want to return values, basically what you can do is talk to a contract that is going to provide you a callback. So you could place a callback, place a lambda expression, or place the address of your contract and say, hey, call me back once you've done something. And give me more information. Now it's a trickier programming model, but in practice it's closer to reality, and it avoids a lot of reentrance debug. It's really harder. It's a little harder to write programs like this, but it's also harder to shoot yourself in the foot. Now one question we do is, what do we do about failures? So let's say that I've emitted this list of transactions, and then some of them succeed, some of them fail. So we could say that if we could say that the entire transaction fails if anything fails. And the problem if you do that is that all of a sudden there's a pattern where you might say, hey, I have a list of people I want to refund, I'm just going to refund them one by one. And if you have this pattern and then someone fails, then all of a sudden, you know, your entire transaction fails. That's not something you'd want. So you could avoid that by not writing this pattern, by writing a pattern where refund have to be like requested one by one, but it's still annoying that you're not able to do that. Or you could say, well, you know, only the individual transaction fails if it fails. But then you lose atomicity. You lose the possibility of saying, I want all these transactions to succeed or none of them. So the right way to handle this is probably to actually treat this transaction as promises, where we give them a callback for a return value and an error callback. And it's, you know, once you've done that, you've basically done continuation spicing style. And the problem is that you get close to actually reintroducing potential reentrance debug, because if it looks like you're just like sending this transaction and then you write your callback function right after, and your callback function just keeps doing stuff, it can look a lot like regular code. So we're trying to find a balance between something that's theoretically sound, that's powerful enough to let people do what they want to do, but also that avoids reentrance debugs. Like, we're trying as much as possible to design the language in a way that will make common patterns hard to common bug patterns hard to commit. One thing that I find interesting is a lack of return value. And the truth is, you very rarely need a return value. The reason that return values are used in something like Ethereum is mostly when you want to use contracts as libraries. And I think that we don't actually need to do that. It's a nice hack, but there's several other things you could do. One is you do data sharing. So if you have a piece of code that matches another piece of code on the blockchain, then you shouldn't pay for storage for it. So that would mean that you could just basically copy-paste the content of a contract and not have to pay for storage because it already exists. So that way you don't have to be dependent on some external resource. You can just integrate the code yourself. But in general, we have pure functions. So it should be possible to register pure functions on the blockchain. You pay a small cost, you register your pure function, and now everyone's able to call it. But it's not a contract. It doesn't have token. It doesn't have a transaction. We know it's a pure function, so we know it's safe to call. So I think that's an interesting, that's potentially an interesting model to have. So that's for calling convention. Gas mileage is something that that we've been working on as well. So we have gas mileage for contracts. It is not tuned. The numbers have been picked basically in order to be conservative, but we can tune them once we do a little bit of profiling. It's not working for when you map a function or you fold a function against a map. So essentially, if you apply a function to this very long list of arguments, it's going to run through it, and then at the end it says, yep, you've exceeded gas, or nope, you haven't exceeded gas. Now, you don't want to do this because you could trick someone into doing a very long validation, and then only at the end would they realize that you've exceeded gas. So you want to be able to exit in the middle. We're working on that. We have big number arithmetic by default in Michelson. All the numbers are arbitrary lengths, but we use naive complexity in our. Wow. All right. So let me try to guess what the German means. Morgen means tomorrow, right? Yes. Okay. So we use naive complexity. You know, like we'll use libgmp. Libgmp is awesome. It implements everything like in the right way. You do multiplication, it's going to be n log n log log n. But here we just make you pay a gas cost of n2 for now because we know it dominates, right? The point right now is to have something that's safe before having something that's efficient. We have a fixed gas cost for typing. So typing actually takes some gas. There's a small joke that you can do on in Michelson. Is let's say that you put an integer on your stack. So you say push 3, and then you do pair. So sorry, you do dup. So if you do dup, if you have a 3 and you do dup, now you have a 3 and a 3 on your stack. Now you do pair. Okay, now you have a pair of 2 3s. Now you do dup. Now you have 2 pairs of 2 3. Now you do pair. Now you have a pair of 2 pairs of 2 3. You do this and you get a type which is exponentially large. So in order to do that, we say you have a fixed amount of gas to type your contract, and it should work for most reasonable contract, but it prevents like clearly malicious contract that try and break the typer. You're still paying for full deserialization of storage, which is not good if you're using maps, which means that right now you can't have a huge map like an ERC20 token would have with a bunch of addresses and a bunch of balances. That's not going to be efficient because every time you run a contract, you're going to have to pay for the deserialization of all that. We're going to make a special hack just for maps, so that because that's the main use case for large data structure, and you'll pay the deserialization cost for the other data. We have a really cool idea for V2, which is hash counting, but we're pushing at that in V2. Okay, documentation work. So we've done a lot more documentation because we're onboarding more people in the team, and so it's useful. One way to onboard people in the team is to have them sit with the existing core developers and explain everything. That doesn't scale very well. It can branch out a little bit once you have more people who know they can explain, but the best way to do that is to actually write documentation. So we started 2 efforts. One is actual doc. So I'm not talking about code comments, but things that really explains the architecture, how things are working. We only have 2 articles. There's a third one coming on proof of stake. So one is on the error monad that we're using throughout the code. That's basically what we use in order to do asynchronous call and pass errors inside protocols, because our protocols are purely functional. So there's like some strange little way in which we're passing errors. And the data encoding, which is how we serialize and deserialize every data type in a type-safe way in the program. And proof of stake I'm working on, it's harder to describe because as I'm writing it, we're getting feedback from the testnet, we're getting more information, and so it also involves the tuning of constants. I was talking about the length of cycles. I'm trying to make a proposal that tunes the constants in a sensible way. We also added a lot more comments to the code. If you download the code from GitHub and you do make doc-html, you should have a full documentation. And I recommend going to, it's hard to find, but if you go to Tezos embedded row protocol.alpha, that's actually the main protocol, and you'll have documentation for the protocol docs. So that's a big effort going on. Proof of stake hardening, so that's what I'm personally been mostly working on. So what do I mean by hardening? So there's several, so I was talking about the networking layer and validation layer and how you can harden your proof of stake here against malicious peer tricking you into performing computation. Another part of hardening is hardening the randomness that you generate on the chain. Now I remember thinking of proof of stake many years ago, and there was a lot of interesting, proposals. There were bad proposals. There were good ones. I remember a few ones which are a little wacky that I've been rethinking about lately. One was, and I'm sorry, I'm not going to credit it, but you can find it. I think it's on the Bitcoin wiki. One was someone who had suggested using the data from state lotteries around the world and hashing it together. The idea being that yes, it's controlled by many people, but there's many different lotteries. It would be very hard for them to try and trick that. There's too much at stake. And so using the outcome of these lotteries in order to generate random numbers once in a while is interesting. One which I find even more interesting would be trying to get a global common source of randomness, like a common coin. So you could look at the sun, for example, and look at sunspot activity or sun activity, and so you have everyone point like some type of physical instrument of the sun, and you get enough entropy from it. You do some processing that guarantees that even if you have some fluctuation with your neighbor, you're still going to converge to the same outcome with high probability. Now that's really cool because no one is going to be able to go and alter the sun, and at least half of the day most people are able to to see this activity. Another one that's been proposed is pulsars. And these ideas are kind of out there, but I really think that they should be explored because, hey, why not? Like, we have this global source of randomness. We should really be using them. I don't know, seismic activities. There's something to be done here. This is not what I'm going to be, this is not what I'm doing. This is not what I'm going to be talking about. So among the proposals for generating randomness on chain, some of the first examples were not like something like NXT, for example. They would just say, well, we'll hash the entire history of the blockchain. We hash maybe the 50 previous blocks, and that gives us a random seed. And the problem is that if you let people do that, you have this, this grinding activity where people are going to search for blocks or change the transaction in a way that alters the randomness and grants them more block creation rights than they should have otherwise. And that's turns out is a very tricky problem. How do you get a group of people to generate a random number? Because so one solution would be you say, okay, everyone commits to a random number secretly, and then we all reveal it, we hash it together, and we get a random number. Okay, problem is that what happens if someone doesn't reveal it? So one solution which was proposed in a paper called Chain of Activity was to use what is called a low influence Boolean function. Meaning you take all your bits and then you put them through some kind of like voting procedure where you group them 3 by 3 and then you get a group of 3 to vote, and then the group of 3s are grouped in groups of 3 and so on and so forth. And in the end, you know, even if you control a lot, it's really hard to control the outcome. So that's one solution. The other solution which the first Tezos paper took was to use economic incentives. Say we're going to play this game of randomness, but you know, if you don't reveal what you've committed to reveal, then you're going to have to forfeit a bond. So it's actually going to be expensive for you to do that. Since then, there's been an approach that's been proposed. It's been proposed mostly by, I think there's been a bunch, but some vocal parties for this type of approach have been Definity and Cardano. And I put them under the umbrella of PVSS, so publicly verifiable secret sharing. They use variations of that. It's not exactly that. But the idea here is I used to plan PVSS for V2, but I realized it was worth having for V1 for security. And so what it lets you do is lets someone commit to a random value publicly, and then distribute shares of that value to end parties, so that stay out of end parties. So for example, like you have 32 parties, and you say, okay, any 11 out of these 32 parties can get together and register that secrets. And the nice thing is you do it in a completely verifiable public manner. So I'm here on a blockchain, I'm distributing this share, and then the network validators look at this and say, yep, you committed to a secret, and yep, you publish valid shares who are validly encrypted to these different participants, and yes, T out of those N shares could reconstruct the secrets, and yes, you know, you've done everything right. And then those parties can also decrypt their shares and publish them, and everything is verifiable. And the nice thing about that is that if I turn out to try to control the entropy by saying, I'm not going to reveal my share, then 11 out of the 32 people with whom I share the secret can come together and say, actually, this is what they did. So if you have enough honest participants in the network, that's a nice way of guaranteeing that you're going to be able to generate entropy without anyone trying to control it. And you know, the approach I've implemented is very simple. It's I follow a paper by Schoenmakers from 1999. For simplicity and expediency. They're a cooler approach that uses pairing cryptography. I'm not doing any of that. This is very, very standard cryptography, and I'm using the Bitcoin curve in order to do it. So that's one addition to the security. I'm currently merging that in the main branch. The other one is the hardening of the seed. So the way that this, you know, the way the seed is computed in Tezos, it's going to give you mining right or baking right, sorry, for an entire cycle, and it's a long period of time. And so even if you could control the seed, it's really hard for you to find a seed that's really, really beneficial to you. In fact, the advantage you gain in doing so is the log of the square root of how many times you try. So you really, really need to try a lot of so you have many, many combinations you can try from, right? If you've baked like thousands of blocks, even just deciding to withhold one block gives you 1,000 possibility. Even, you know, choosing to withhold 2 blocks give you 1,000,000 possibilities. So you have many, many possibilities in how you could play this, but you have to go through all these possibilities. So one hardening we can do is say, what if it were expensive to derive the seed? You know, not so expensive that you can't do it once for the network, honestly, but very expensive so that not so that it's not easy for someone to grind. So one simple idea would be to hash the seed many, many times. So you take the seed, you hash it 1,000 times. Now that works, and it's expensive to compute, but it's also expensive to verify. If you're following the chain, now everyone has to redo the same work. It's a waste. Another option would be to solve a proof of work puzzle. But the problem is that there's many solutions. There's not a single hardened seed that could possibly pass this difficulty threshold. So the approach I'm taking is to generate a random discrete logarithm. Oh no, I said a DLP problem. That's like a pin number or an ATM machine. So you generate a random discrete logarithm problem. And the nice thing with that is that they're very hard to solve, but then there's a unique solution, and once you publish the solution, it's obvious that it's a solution. There's two ways you can do a random DLP problem. They both have advantages and inconvenience. The finite field approach is you take a soft seed. So you have all these people that do this randomness procedure, and they're honest because otherwise they lose their bond, and because otherwise there's this PVSS procedure that guarantees that all these shares are going to be taken together and you're going to get all the entropy. So you have that, but still it gives you just a soft seed. Then you find a safe prime based on this seed with about n bits, so n is a difficulty parameter. And then you find the first two generators of the cyclic group of order P in that finite field. And you solve the DLP with respect to those two generators. Very easy to generate the problem. You can generate that very, very quickly. The problem is that if you want to write a Baker code that actually lets people solve that, then it's a very, very complex algorithm that are, the optimal algorithm for solving that, I think, are in the cubic root of the number. So it's x over 3. And I think the number field sieve algorithm is non-trivial to implement. There's some software who do it. So you don't really run and say people like, hey, run your baking software. And by the way, once every 11 days, you need to run this complex software produced by INRIA or by some research center in order to crack this DLP problem. So we could do it on an elliptic curve. So we can't use always the same elliptic curve because people could start building rainbow tables. They could just memorize all the solutions. So you generate a new elliptic curve, and then you hash 2 points to the curve, and you solve the DLP. Now, the nice thing with that is that the algorithms for solving DLP on elliptic curves are still pretty simple and not very sophisticated if you don't have any structure on the curve. So at least you know that it's not hard to implement a really good solution. The problem is generating the problem. If you want to generate an elliptic curve on which you're going to solve this DLP, you want to calculate the order of the curve. You have to use something called the Schutz algorithm. And Schutz algorithm is not trivial to implement. So we could use it as, we could, if we find a good implementation that we can use as a library, we can do that. I am not going to implement Schutz algorithm in OCaml for V1. That is not a good idea. So hesitating between these two to harden the seed. The idea would be that it might take someone like an hour of computation over a period of 10 days in order to produce a seed, which is fairly reasonable. But if you're trying to grind stakes, it becomes extremely cumbersome to do that. You can still parallelize it, but you have all of these other things getting in your way. You have PVSS, you have the fact that there's economic incentives. So it's really a belt and suspender type of approach. I know it's not very clean. You would rather have a very, very simple system with just like one protection. But I believe in layers, and then in the future, if we believe that some layers are unnecessary, we can remove the layers. Let's have as many layers as possible at first. Okay, so this is what we're working on in Paris. I'm helping the Parisian team work on this, but there's also a lot of great community work, and I'm not going to, I don't know how I'm doing on time. I'm not maybe going to do it fully justice, but I want to present some of the stuff that folks are working on because I think a lot of it is really cool. I'm going to forget some projects, and I'm sorry for that. If you have a cool project that I don't list tonight, please let me know. I want to be touting your work. So let's start with just like the community and help site. This is more of a public service announcement more than anything else. We're on Reddit, but there's also Jonas Lames, who's done a tremendous job at building forums.tezos.community. Great community here. We're also on Riot. This is, so I say Riot. Okay, so Matrix is a Jabber-like IRC system, and they call Matrix, which is a bad name because you just search for Matrix and you find a million things. Riot is the name of their client. So they have a web client. If you go there, you'll find a lot of the community, especially the development community around Tezos, hangs out in Riot. There's two cool websites, Tezos.help and Tezos.rocks. they're basically list of links on a lot of projects and a lot of different websites. So if you want to know cool things which are being done for Tezos, there's a good place to look at. Block Explorers. We have 3 Block Explorers. The earliest one from Fretzy, who's been following the project for over a year now, ostez.com. It's like Tezos but reversed. He has a pretty full Block Explorer that will let you see not only the main chain but also the different branches. There's tezoschain.io. So this one also lets you explore what's inside the block. You can see the different transactions. It looks pretty sleek. The recent upcomer is tezos.idea, which was released recently. So check out these 3, and it will give you a sense of the AlphaNets. Yeah, I also realize that a lot of people don't know that Tezos has a live AlphaNet, but we do have a live AlphaNet where people are writing contracts, people are testing contracts. It runs, you can send transactions. So there's a lot of it that's out there and working, but it still needs to be hardened. Like there's a big difference between having something that works and having something that's battle ready to be live. If you're considering building a Block Explorer, because I know some folks are building Block Explorer, if you're one of the people building a Block Explorer, start by building a caching database. Don't try to have like direct requests to a node, because the nodes don't try to index information in a way that's really helpful to you. Hey, here's a cool thing. The client can generate smart contract traces. So if you want to see how a smart contract was executed in a block, there are some RPCs in the Tezos client that will actually show you that. I don't know that any Block Explorer shows this right now, but that would be, I think, useful. And offer a preview of the blockchain. So Fretzy is showing you the different heads of the blockchain. I think that since it's early days and we reboot the AlphaNet sometimes, so sometimes you'll see when the network gets a little thin, you'll see forks, and it would be very helpful to kind of like be able to really visualize them directly. Dev tutorials, there's 2 great dev tutorials. The first one, getting started with Tezos, it will show you exactly how to run a node on the AlphaNets and then write your first contracts. And then once you've done that, go to mikkelsonlang.com, which was built by Milo Davis, who sits with the French team. And it's a blog post series, but he's done this on his own time. It's a blog post series showing you a lot of contracts for an entire month. He did 1 contract a day in Mikkelsen, so it's one of the best resources out there for writing contracts. Languages. So we have a bunch of languages that compile down to Mikkelsen. There's Liquidity, which is made by OCaml Pro. It looks a lot like Camel, compiles down to Mikkelsen. There's Phi by Steven Andrews, which looks a little bit like Solidity. It's supposed to look like JavaScript and Solidity. Take a look at it. I think it looks better. Lamtez, which I didn't know until fairly recently, also ML-like by, I think it's Fabien Leto or Fabrice or Fabien Leto. And Juvix, which is by Christopher Goes, and it compiles a language that looks very, very close to Haskell down to Mikkelsen. So you don't have to write directly Mikkelsen. There's plenty of options if you want to be writing smart contracts in Tezos. Wallets, there's Tezos.blue, which is a prototype Android wallets by Andreas Hassman. Tezbox is super interesting by Steven Andrews again. So Tezbox is a Chrome plugin that works like MetaMask. I don't know if you guys know MetaMask of Ethereum, but for Tezos. So it adds itself to your browser. It injects code in the page so you can communicate with a Tezos node in JavaScript in the browser while at the same time being able to send transaction on the AlphaNet. So check it out, Tezbox. And Tesla.io, I don't know who's making, I'm not sure who's making Teslets, but it's an iOS wallet that connects to the AlphaNet. Delegation. Delegation is a tricky thing. I didn't know if I was going to mention delegation tonight. Why? Well, it's important to be neutral. Delegation is something that's going to affect decentralization. If I say like, hey, there's a delegate service, it might affect the balance of delegation, so neutrality is important. On the other hand, I did mention wallets, and I think a lot of people building wallets are probably going to end up, partnering with delegation services, and I want to be mentioning wallets. I also don't want to say, hey, you know what, if you're a delegation service, the only way I'm ever going to talk about you is if you kind of hide yourself into a wallet. So I don't know, I've said before I was not going to mention delegates. I think it's still a very small ecosystem right now. It's not going to, it's not going to have a lot of sway. So I'll mention 3 people working on delegation, and I hope I'm probably forgetting some people, and I will add them. So there's Bo of Tezigator, who's doing a great job thinking through his setup. Microsoft delegate Mike Mohonan, who's been working on this and following Tezos for a while. Chainomatic. I just got an email about another delegate services. So there's a bunch of people who are working on providing delegations. Think of it as the equivalent of mining pool, but for proof of stake. Stuff I'd love to see. We have a lot of ML-like languages in Haskell. I'd like to see a simple Pascal-like language. I like Pascal, or maybe like a BASIC, but like more like a type BASIC. That would be great. Easily deployable baking solution. I think Stephen Andrews has mentioned he was working on something like this. We would want to make it easier for someone to just be their own baker. Maybe it could be an appliance, something you just plug at home and you just do baking. Maybe it's just like a very, very clear tutorial on how to launch this. Integration in Bolos, the operating system of the ledger. A Michelson IDE, we have the annotation mode in Emacs, which is great, but a full-blown IDE, and an optimizing compiler for stack manipulation in Michelson. And that's it, so I'm going to take questions now.
Thank you. Yeah. So we'll take 2 general questions. Afterwards, the wine is waiting, so he'll be here after. If you have further questions, you can ask him personally. Yes?
I feel like I'm the only one out of the group, but what is Tezos?
Oh my God.
Sir.
I should have started with that. Tezos is it's a smart contract platform in the same vein as Ethereum. But one of the peculiarities of Tezos is that it has self-governance, meaning that you can, instead of hard forking in order to have upgrades, you can propose upgrades on-chain, and then the stakeholders can vote on the upgrade, and if they vote for the upgrade is automatically adopted in the code base. Yes?
Sorry. How can I be part of the proof of stake system in Tezos?
Concretely, easiest way right now is join the Riot channel, start talking to people who are working on baking, and they'll get you started.
All right.
Arthur, congratulations first. I think that's super stuff. We read a lot about Tezos, but it's really for maybe the wrong reasons. So congratulations for the work that you're doing.
Thank you.
I do have a question, though. When you build a community and you try and propagate a project like this, it takes funds. In terms of the Tezos Foundation, are they obliged to fund whatever project you're building forward? Is there some kind of route from that money into what you're trying to do? Because it is going to cost money to do what you're trying to do.
Yeah, I mean, the thing is, like, development like this is not actually necessarily that expensive. You know, you want to have a small, committed core dev team, and you can do a ton of work and have a great community. In terms of foundation, my understanding is that they have a legal mandate to spend the fund towards the promotion of the Tezos network in particular. Yeah.